Hey, and welcome back, everyone. So, to those who are new, we're doing these streams here every week, and what we're trying to get our own firmware to run on the VisionFive RISC-V single-board computer. So last week, we had a look at the vendor-supplied bootloader, eventually, where you can just download the source code from them. And today we're going to try to run that. And at the same time, we also wanted to take a dump of the existing mask ROM that is already in the chip on the board. And so I have prepared a bit and dumped that already. And you can already see that here in the terminal window that I'm sharing. So let's have a quick look at what we have here. And then I will show you again how I obtained that. And let's start off with having a very brief look at the hex editor here, or well, only hex viewer at this point. So here on the left hand side, you can see a bunch of values here. And on the right hand side, in the last column, you see ASCII representations of what you're seeing. On the very left, these are the offsets in the file that I have here. So essentially this is just a hex viewer. And now if you know the RISC-V instruction set, you can technically understand what it's saying here. So these are all very low level instructions which are being interpreted by the machine. And now the question is, what does this here do anyway? So what we figured out already is there is a recovery bootloader in the firmware which you can talk to over one of the two serial ports on the board. So there is a special one just for this recovery here, and it would be running this very code. And before we try to interpret this, let's actually have a look at the size of this file. So I will close this now, and you can see I called it maskrom.bin. So this file maskrom.bin is not very large. It's just, as you can see, 32 kilobytes in size. And that is also the size of the SRAM on the chip. So that is the RAM that is built into you could call it CPU. Today it's called SoC. So that is the processor, which also has peripherals on it. And why am I telling you this? Because you need to understand, if you want to dive into firmware, you have very many pieces that you have to deal with, and you start from one stage and always hop on to the next one and the next one until you eventually end up in your operating system. And you have to start small because in the beginning you don't have much memory. So you only have this SRAM that I mentioned, and this is where this code can run. So this here really just fits. But I had a bit of a closer look actually, and it turns out that it's even smaller than the file. So there could have been much more in there, but it's actually good that it's not that large. So we can look at that by using the Hexdump program, for example. So Hexdump, similar to XXD, what I used before, will print out the hex values of the file. But it would omit whatever is just zeros in there, or just FF, for example. So when we run this, you see here in the end, this here is the last offset being printed, 2FE0. And 2FE0, let's quickly evaluate that in my favorite calculator, which is Node.js. So this resolves to about 12 kilobytes, right? Which means we're actually only using a third of the available size. And now to get a bit of a clue what we find in this maskrom, let's use another tool which is called strings. And the strings tool will tell us, every printable string which is in the file, sometimes also a bit more like things which could technically be a string, but it doesn't matter too much here now. So if we look at this, first of all, it all fits on one single page, which is good here. And second, we find a very few messages only, which is very much what I would expect from a recovery bootloader. Now, one thing, we've already seen this last week, is the copyright SiFive here. So this is what we see when we turn on the device in the bootloader mode. Then we have this here, load, which is the command that we run to tell the device to load to a specific address. What we're going to send it over the UART, and for that we would use the second UART, or serial port if you will. So not, now I have to actually correct myself. We actually do use the same one as the recovery bootloader. Okay, so we would say load, then the address to load to, and for the address we would use the address of the SRAM. I've already prepared a few notes so that we can do this as an example in a bit. Well, and here you can also see there are some messages, which is the feedback that we can get while loading this file. So let's now have a look at that very quickly. This will be about the same as what we did last time. So here at the top I have one terminal. I have a split view here. So this is now one of the serial ports that I have connected. This is, you can see TTY USB 0. It's one of the USB to serial devices that I have attached to my laptop. And this is connected to the recovery bootloader's UART pins. Now when I run this, I need to be careful with the baud rate. So I already messed this up a few times. We need to pick 9600. It's a very low baud rate, but that's perfectly okay for the recovery bootloader. Okay, so let's enter this mode here. And now I'm going to keep the boot mode button pressed while powering on the board. And just as last time, we see this welcoming message again, which is saying copyright SiFive. Now what I've also prepared is a few binaries, so I will show you this. I have this one, which is the recovery bootloader, and I have another one, which is called second loader. And we will get to second loader in a bit, but first we will start off with this one here. Now the question is, how do we load this? So there are a few options. I could now manually type in the address here and say load whatever address, and then use the file transfer here in Minicom, which we can reach by saying Ctrl A and then S, and pick X modem. Now the problem is there are some settings necessary, so I already tried this before, as you can imagine, but it hasn't worked right away. But we are very fortunate that somebody prepared a tool for this, which we're going to use instead. And to be able to use this tool, you will actually need to close this here now. So I'm going to do this now. I'm leaving. And I have prepared a script which is called run.sh here. What this run.sh script will do is the following. It will invoke the tool that we have in here. It's just called JH7100 recover. Then we pass the name to the serial device that we want to use, my USB 0 that we already saw in the right hand side. And then I can supply a path to, well, the recovery bootloader first of all, but then also another bootloader binary and the DDR init binary. So as you can see, I have commented out a few things here. So let's start with this right away. And for that, I will run the script. And now I will reset the device and keep the boot mode button pressed again. I have to do this because the device is, the script here or the tool is actually waiting for the copyright SiFive message, and then it would start with a transfer. All right, so that's pressed. And now on the left-hand side, you can see the transfer in progress. It takes a while, even though it's just 22 kilobytes or 22,000 bytes roughly. It takes quite a long while, and that's due to the low baud rate. And well, it's okay for the time being, right? It's not like we're going to run this 1,000 times or something. Anyway, so this is now saying enter recovery mode. It also says firmware update completed. That is not strictly the case here right now, but let's ignore this and now let's hook up the serial. So yeah, now I'm in Minicom again, and now from Minicom I want to now use the file that I just transferred. And so what this is the recovery bootloader that we cloned last time from the repositories. So technically I would now have seen a menu here, but because now the recovery tool and Minicom, they would both need to access the same TTY USB 0 device. That doesn't really work to run both in parallel. So the quick way is to just, use the tool on the one hand side and then later on start Minicom. So I will now hit a key and I will just, type anything. Let's say I will type 3. And now this here says, oh, I actually need to select 0 or 1, and I should select the function to test. But I have actually entered a hidden message here. And if we want to see the initial menu, I think we can just type anything. Uh-oh, that was wrong. Okay, I think we need to start over now. I messed it up again. I'm sorry. But that's what we're here for, right? We're learning. So I'm putting the device back in recovery mode and running the script here. So again, we need to wait for a few seconds. And then we can run Minicom again. So the original prompt was just saying you have to type 0 or 1 for the recovery mode. And that's in fact the same that we also tried last time, which was listening on the other serial port. So that's the one I've already connected below here. So anyway, let's connect back here. I will just quickly clear this. And now instead of 0 or 1, I will actually type 2. And what you can see here is I actually I hit this here. Secrets are inside. That's a message I already added to this recovery bootloader. So that is not in the stock code. Okay, so what we just did was we just ran our own code on this machine, which is something that I just compiled myself, but I also made my own changes to it. But now before we get to looking at how that worked, like building it and so on, I want to quickly give you a recap on how I dumped the mask ROM. Okay, so as promised, I will now push the reset button here, and at the bottom we see we're booting into U-boot again. So that's also what we did last time already. And then I did something, and for that I have my notes here. So the first thing I needed to do is I needed to set up a network here. So I have a few network adapters you can see here at the bottom. This is the one I'm going to use now, 192, 168 and 22.1. This is my IP address here on a special network port that I have just quickly added here. So usually I would use this one. This is my internal network. But yeah, for development purposes, I just want to have this board here isolated. Okay, and as I told you, I need to run a Tftp server. So if we look at, oh, I actually already typed this at this here. So this is what I'm running, the HBA Tftp server. This is something that you can, if you run, for example, Ubuntu, you can just install from the stock repositories. If you search for TFTPD, you will find this among the services. Now, I've set it up so that I will have files in this directory /serve/tftp. There is already a file in there from previous experiments, but what we're going to do now is we're going to add something. So again, back to my notes. In U-boot, I can run the following command. I can say tftp put, then give it a memory address and a size, And then I can give it a name for a file to have on the remote side. Okay, but before I'm going to do this, I will also set the server IP here. So this is something you could also technically provide with the tftp put command, but yeah, we'll just do it in these two steps for a bit more convenience. So I've set this server IP environment variable. In Uart, there is a larger environment that you can define, and there is already a bunch more defined, but we're okay with this one here. We don't need much else. And now I'm going to say tftp put. And oh, what you can now see is, oh, IP address is not set yet. That's on me. So what I've just missed out is I'm also running a Dhcp server. And the Dhcp server, this will now obtain our own IP address. And our IP address in this scenario here is, well, almost the same as my local machine here. It's just with a 100 instead of the 1 at the end. Okay, so let's run the command again. And now you can see it has already happily transferred it. So this is much, much faster than the X modem transfer that we had over the Uart, right? So yeah, if you ever downloaded something from the internet, let's say in the very early days, like in the 1990s or something, that was also horribly slow. But today we have very, very fast interfaces. So that's much, much faster than any serial line that we have now. Anyway, so if we look at the serve tftp directory now, there is this new file which has exactly the name that I also specified here. Well, or specifically in the full command here. Okay, so this is what I already did in preparation for today. And that is the very file that we were looking at here and from which we got the strings. So what we could technically do now, we could reverse engineer this code here, since it's not much anyway. I'm just scrolling down here, and I guess I would be done in like a few seconds. So we already saw this, right? There is not much in here. It ends at this offset here. So yeah, but I actually don't really want to do that because we have good documentation on this platform anyway, and there will not be anything really interesting in here. So what the recovery bootloader really does is it just allows you to transfer a file, and that's it. And then you can run it from memory, right? Okay, so the recovery bootloader now, which I had already prepared, this is coming from this repository. This is at StarFive Tech bootloader recovery, just like the directory here, so I haven't renamed it or something. But I did make a few changes, as I told you, and let's have a quick look at that. So there is this file here, source boot main, which is the main file. Let's have a quick look actually at the directory here and then also at the source directory. So there is this here. There is one directory which is called BSP. BSP is a very common name. It's short for board support package. That's a common approach used by chip vendors to give you ready-to-use code, but in a sort of in a library way, together with the board that you want to use. This debug directory here, this is already output. So when I run the make command here to build this, I will get my output here. And then the actual interesting part is in the source directory, src. Now let's have a quick look at that. There is 3 parts. One is boot, which I told you is the file to edit, or the files to edit are in there. There is common and driver. So let's see, what drivers do we need anyway? There is one driver for the SPI, the serial peripheral interface, which is where the flash part is that resides on the board. So through this interface, we can write to the chip and write our firmware image, for example, or read from it or whatever. There is a timer. So timers, we already had a very brief look at that last time. Timers are essential to computing, right? Like everything that is triggered with a delay or something can be run with a timer. Then we have Uart, the part which is below the serial port. So this is like the physical interface, if you will. And then we have Xmodem. So Xmodem is what we're using for the transfer. It's not really important what exactly this means right now, but it's just for our file transfer, what we used the tool for previously to send over our own binary to the chip. Okay, so what do we have in common? In common, we have these header files. And well, there is also one C file here. It's not the most common, if you will, sorry for the pun, approach to doing this. There are also projects, which are a bit more like this here. I would say a very loose structure. Usually would have header files in a directory named include. But this here works perfectly fine, and it's a small project anyway, so there are no big concerns about that. So there is another C file, as we can see. This is for printing to the serial port, and then this sys.c. I imagine this is like early startup bits, maybe. Now let's look at the most interesting part, which is the main part, gluing everything together. So there are two files. One is called start.s, which is a very common name for the first assembly instructions that you would usually use. And then we have boot main.c. You could also just call it main.c. It doesn't really matter here. This is the main file, and that's the one we're going to look at. So let's have a look at this here. So this is coming from StarFive technology. It's released under the GPL 2.0 license, which means we can just use it as we like. But if we make any changes and publish a binary to someone, we also need to provide them with the source code. There are some vendors which are not doing this, so that's why there are some lawsuits for actually getting the source code that I should be able to obtain from them. But yeah, let's put that aside. It's one of the common issues with licenses and software. Anyway, we're happy that we actually have this here. And so we also have a good reference for writing our own code, right? So this is very helpful. Now let's have a quick look. We see the sys header file here is being included. So we already saw the sys.c file, and there was also a sys.h file. The interfaces that we need, the Uart and the SPI, are in here. Also something for the SPI flash. And then a few other things that we will need for running the system. And now if we look here a bit further down, we will find a main function. Or do we find a main function? Let's actually search for the main function. No, we don't. And in fact, you don't even have to call a function main. So in the C programming language, it's more like a convention to have a function named main. But if you don't target a system, you can pretty much set up anything. So now before we scroll too much through the file, let's actually boil this down a bit. So let's have a look at the assembly file, because this is where we define things like the function to execute after the assembly code here. So there is this function here. It's called start boot main. Okay, that is interesting. And then there is a bunch of assembly instructions in here. Now, if you know x86 assembly, you can probably understand some of this here. These instructions are now for RISC-V. But yeah, the principle holds. Like this here, for example, is load immediate to load a value into a register. The add instruction to add two values, like from one register and another register, and so on. But we were interested in this here, so I quickly detected this. If you see a J, J is for jump. This is for jumping to the main function. And if we look at this here, oh, it's actually still within this file here, which is also not too uncommon. So let's see where this continues. So it's doing a bunch of things, and eventually it calls something called, it's called boot main, and main with an uppercase M. So let's see where we find this in our source directory. And here we are actually back in our boot main file. So let's open this file again and let's jump to the boot main function. And here we go. So yeah, if we had read this carefully, we would probably have guessed that this here is the entry to all the C functions. So what does this simple program here do? The first thing it does is it initializes the Uart for us. So this is a very important thing because this now allows for us to print something to it. And the first thing it's doing here, it's printing this here. And technically we could have seen that, but as I mentioned, so we have this one tool for, transferring the recovery bootloader, and then we open Minicom again. But in between was actually the moment where this message here would have been presented. And so what you can do, what you can see is, there is this here I already added. It's called secret message. And then we have this additional here, what I just did. So when I say I select 2, this here is the comparison. If you enter a 2, then you will see this message secrets inside, and if it's above 2, you would get this message telling you to select 0 or 1. It doesn't mention the 2, but actually the initial menu does. Now let's quickly get back to this here and enter the recovery mode again. So I will close this here again and enter recovery mode. And I will transfer back the file. So if I had just hit return, I think we should have seen this message here. Or if we select something which is also a number. Yeah, there is this thing here. Okay. So let's see what happens. We're running Minicom again. And let's enter something like 5. Oh well, 5 doesn't do anything. And in fact, nothing is doing anything. Well, it's a good question why this is the case now. Huh. Puzzling sometimes. Okay, maybe, I don't know what happened. Let's just run it again. So yeah, I promise to be a bit better prepared this time. I hope you can understand. This is all a bit fiddly, so yeah, it's not too easy to follow through sometimes, even if you have the manual, right? And as you could see last time, the menu is already full of pictures and nice explanations, but still not too easy. Okay, so let's try entering 2. Okay, and there we have our secret message again. Now what happens if we enter 3? It says select 0 or 1, right? Okay, but I actually wanted to see this nice message again here, which should happen continuously. So how do we get to this point here? Is that something they had in mind? So we can enter something like nothing. Then we get back this here. Yeah, and unfortunately this also happens. Okay. Yeah, then let's stop here for the time being. I actually don't really want to fiddle with this much anyway. But let's actually have a look how the code here works in general. So we have these few messages, a very simple program that is running. And depending on what we select, we get something printed, or this function is being run here. Up data, yeah, I guess they were not English native, so there are some typos or grammar errors here. Like it's actually saying up data every time here. Let's just ignore that. So this is the function which is just evaluating the number that we entered if it wasn't the 2 or anything above 3. So it would call another function again, and this here would run two different things. So we can update the secondary bootloader, or we can update the DDR init. And the secondary bootloader is the second binary that I had prepared. So this is this file here. I called it secondloader.bin. So we could now also use the tool that we used earlier to run the recovery tool here to also send this secondary bootloader file, right? Okay, so what does this actually mean? So when we run this would be defined in one of the header files, I suppose. Yeah, it's just the number 0 behind this, right? And the other one, I guess, would be just the number 1. It's a bit odd how they made it. Yeah, that's okay. Okay, now I see. So these are actually the start addresses in the flash part. So this would be at the offset hex 10,000 in the flash part. Okay, so that means we have up to hex 10,000 or 16K. No, hang on, 64K for the recovery bootloader. For the secondary bootloader. That would be this one here. So let's actually verify, because sometimes I get lost a bit with these numbers. So hex 10,000 is 65,536. Right, so this is 64K. So if you want to remember a few of these, 10,000 is 64K and 1,000 is 4K. So one of the digits is for, goes up to 16, which we cannot represent in a single digit. So we're using letters like up to F. So this means if you take, if you multiply by 16, you just hit the next digit, right? So if 1,000 is 4K, then 16 times 4K would be the next digit. So that gets us the 64K. All right, so back to this file here. Now this function, update flash code, what does it, sorry, update flash. So this is where we pass the address to write to for the flash part. So what does this do? Again, it expects us to send a file using the X modem transfer, which, as we saw, is a very, very slow mode for transferring files, but that's okay. Now what I want to do is the following. So I want to flash the second loader.bin file. But this here is now what I just pre-built, and it's really just the stock source code. So this would just get us the very same thing that we already had. Let's maybe, for the sake of the example, actually do this. So what I will now do is I will uncomment this here. Did I call it bootloader.bin? No, I call it secondloader.bin, and it's actually also up here. Okay, so let's run this again and bring the device back into the bootloader mode. And let's see if both files are being sent and processed. If so, I would imagine that the second loader would now continue down here. So yeah, on the second Uart. Let's see if that actually happens. So the good news is that second loader.bin is just 10K in size, so it doesn't take that much longer. Oh wow. It says cannot open file. That is a bit unfortunate. Now, why can't this tool open the file? Oh, and you can also see this here, secret message. Now this is actually coming from our little hackery, right? So yeah, this is already our modified recovery bootloader. And now let's see what's going wrong here. So // oh, I see what I forgot. I forgot the FW here. Yeah, I put all the binary files in this FW directory so that it's easier to access. Okay, so let's run this again. Let's reset and wait for the transfer to finish. So what this is now going to do is it's running our modified recovery boot binary again, and then it's going to write the second loader bin file. So this file here to the flash memory at the offset 0. So that's what we just saw here when we had a look at this. So that was the flash second boot start adder 0. Okay, so now we did this. We wrote another file. And now let's reset the board, and we should see on the bottom right side what we just flashed. And well, it just says bootloader version something, right? And then DDR something. So let's have a look at this bootloader version thing. Do we actually find this in the bootloader source code? So that is what I prepared this here for. This here is second boot, so this is where we should find the string. Let's see. And here we go. Oh, it's actually written in assembly. So now this is getting a bit interesting. Let's see. We're searching for something with version here. Okay, and it's using the print. Oh wow, this is amazing. It actually looks a bit more like C and assembly mixed. Okay, that's okay. So now let's modify this here. And instead of bootloader, let's write something else. Let's just for the fun of it, let's call it booploader now, because it's just funny, right? And so what we're now going to do is we're going to rebuild this. And you can see I have the script prepared here. This build script is just doing the following. It's using a local copy of the toolchain that you can obtain from VisionFive. So I did this because last time we actually tried compiling with the toolchain that is shipped with Ubuntu, but it didn't know some of the options. But here it just works. So when we now run the build.sh script, it says nothing to be done. That's because I already built this, and apparently the scripts here aren't really prepared for change detection very well. So let's run build.sh again, and now copy this this binary. It's called bootloader something.out. Yeah, I'm just renaming it to a different file. Okay. So now we're going to flash this again. Which again will take a few seconds to transfer. And when we then reset the device, instead of bootloader down here, we should see booploader. And yeah, then let's have a closer look also at this bootloader here. So now the interesting part is we already had a very brief look at that recently. We're realizing now that we have these different stages, and if we want to mess with something, we actually have to use all of these different repositories and so on. That might be a bit confusing. So especially for development. I personally prefer to have things a bit more self-contained. And that is what we can do with the oreboot project. And I will get back to that in another stream, not this time. Okay, so let's reset the board. And we now expect to see booploader instead of bootloader. And apparently that hasn't worked because it's still saying bootloader. So what went wrong? Let's see. So we have FW here. there is a file second loader.bin. This is the one we just created. The timestamp looks okay. 2039, 2049, 41. That's what we just had. But why did this happen? So let's check. This here is the file that we got. Okay. Now, do we see a string in here which says booploader? No, it actually says bootloader. Why does it not say booploader? I have a suspicion. Look, it changed back to saying bootloader. So my suspicion is that this is actually a generated file. And oh wow, there is something called convert here. What is convert? Okay, so whatever is going on here. I see. This is actually an intermediate. Okay. And there is also this here, fsz.sh. Let's have a look at that file. This is quite an obscurity, to be honest. Okay, so this is probably part of the build process because we have seen something similar to this here. So let me clean again. So when we were in build.sh, we saw these messages here like in file, out file. Okay, wow. I see. Okay, so I got it. We're in the build directory here. But what we would actually have to edit is the source here, and this is the boot directory, just one level up. But the make file is for some reason in this build directory here. That's okay to have it a bit more self-contained and within this project. Okay, so let's go to the bootmain.c file here. And let's search for bootloader here. Right. So now we can say, okay, now we can actually say bootloader. Yeah. Now let's build again. And now actually the detection worked, right? So we had already built this, but now we have changed a file and we ran the make tool again. And well, make has detected the change. And that's because this time we changed the actual source and not an intermediate file from the build process. Okay, so what we can now do again is we can copy this back. We can reflash this using the tools that we have here. And apparently what also happens is something that I find very nice. It appears that the mask ROM, if we do not enter the special mode for recovery here, apparently it really just starts executing at address 0 of the flash part. So that is very, very handy. And we can actually verify this. So sometimes you need to have special headers or something, but I guess not in this case. So if we look at this bin file, yeah, these all look like instructions. It doesn't look like there is any special header or something. Okay, now let's hit the reset button again, and now this time we should actually see bootloader. Oh, and there we go. Now we have our own modified copy of the bootloader. Yeah, and instead of boot it says boop. Which is funny because I actually have to press these boop sort of buttons all the time to enter this loader. All right, so yeah, that's also what I showed you in the camera last time. So on the board, we have these button here, which is the boot mode button. And right next to that is the reset button. So every time I said, okay, I will enter the bootloader mode now, I was keeping this button here pressed, and then I pressed the reset button. And for the serial connection where the transfer happens, so everything that we see up here, or well, on the left-hand side, this is this serial port here hooked up, where it says debug. Well, it's cut off here, but it does say debug. Okay, so that was also very interesting. So we've done two things now. We have modified the stock recovery loader, and we have modified the stock bootloader, well, the so-called secondary bootloader, which we now renamed into a booploader, which is sort of hilarious. Okay, and we could also see, let me close also this here on the left-hand side, we could also see that both structures are very similar, and for that I will go up a directory again here. So this here is on the left-hand side, we have the structure of second boot, and on the right-hand side, we have the structure of the recovery bootloader. And if we look at the source directory here, we have the structure boot, common, and driver, and the same is here, boot, common, and well, what we have in driver here, well, here we have it in SPI, timer, and UART, right? So this is very much what we had here, except that we also had Xmodem, which we need for the recovery bootloader, but we don't need it in the eventual bootloader. So yeah, you can already see one reason why we are nowadays not using the C language to write our firmware, but instead we do it in Rust. And that is mainly because here in the case of C, there is a lot of copying around happening, right? So we have this same stuff that we have here on the right-hand side. We also have it here on the left-hand side. Now, if you, if you set up a bit of a more fancy repository, you could probably make it so that everything is contained in one repository and you can actually share those things. But C doesn't really have this concept that we have in Rust for, sharing code as modules or crates, as it's called in Rust. So if you have already done something with the Rust programming language, then there is this, well, it's a registry, that's what we call it commonly in software development, where people can upload their own crates, and then there is a nice website you can browse. It's called crates.io, and this is where you can find all the modules and programming libraries that you can just use in your personal application. So yeah, instead of having to copy these things around here, we would just import a crate. We are going to do this in one of the upcoming streams. So yeah, but for the last part of the stream here today, I actually want to have a closer look at this here. So I want to have a very brief look into the Uart driver. And I also want to see it on the right-hand side for the recovery bootloader. And let's see if they are actually the same or if there are some differences. That is one interesting thing. And the other question is, how does the Uart actually work? Can we simply write our own driver so, that we can just write our own Hello World program in Rust next time? And so let's see. Oh, actually, let's do the following. Let's list all the files in Uart. And also here, using the ls command with the L switch so that we get nice listings. And we can see they are not exactly the same, right? So here the C file is 7961 lines, and here it's 7396 lines. Yeah, which shows yet another downside of the C ecosystem, right? So they are not in fact sharing the same code, but something that is somewhat different. Now let's have a look at that. So the C file, I'm not concerned with the header file right now. We can see it's about equal in size, but that's okay. It's mostly definitions, which I'm not that curious about. I want to follow the actual flow. So C reports require some setup usually, like entering a certain mode. You have already heard about the baud rate. Yeah, it's spelled almost like this here, but the A comes first, so this is actually a typo. Anyway, so we were using the very lowest one for the recovery bootloader, so to transfer it over, that was 9600. Higher speed baud rates nowadays are, well, usually we use 11500. That's like the most common one, I would say, at least the one that I see mostly. But if you want to go really high speed, you can even use this here, like, what is that? 2 million, which is already quite fancy. I have seen these higher baud rates already for some devices, but yeah, it's rather rare, let's say. Okay, so this here is very interesting. So first of all, we see a lot of defines here. This could as well be in the header file, right? But it's in here, which is nice, so that we can look at it together with the code. And let's look on the right-hand side if we see the same definitions. We probably should. Or maybe not. Maybe here in this case, it is actually hidden in the header file. Okay. Yeah, then let's actually open this file. Let's see what we have here. Right, and that looks very much like on the left-hand side. Okay. So yeah, a UART has lots of different registers. They are described here, and they are necessary to be set up in the right way. And then for the extra driver, you would need some of those. One of the registers that you would use, for example, is the line status register. You would use the line control register. So yeah, if we look on the left-hand side, we will probably see those. Let's look for the line status register, if that is used here. No, in fact, it's not. That is interesting. Oh, now I'm actually realizing that I was looking at the header file all along here. I'm very sorry, I thought I had opened the C file. But that is also interesting. So we do in fact have very similar header files, but the difference here is like we have the sys header also included again here. And I guess a few other differences. Yeah. Okay, so let's do this the quick way. We will use the diff tool. So with the diff tool, well, let's actually use the Vim diff tool because Vim does it in a bit fancier way. Let us look at the second boot UART header file. And on the other hand, we want to have the recovery bootloader drivers UART header file. Yeah, it's all saying that these files are already open, but yeah, whatever. Aha. This is interesting. So yeah, on the right hand side, we have additional defines. And so we have a sort of second copy of all the registers. And they're just multiplications of the registers above. And they're multiplied by UART reg adder interval. So what could that be? Well, we will find this by searching for it. And we will search for it in the bootloader recovery thing. That is just the number 4. So all the registers here are multiplied by 4, which is interesting. So I have seen this before where you can have UARTs which can hold a single byte per register, and there are also some which can have 4 bytes or 32-bit registers. So this looks to me pretty much like that. And now I'm wondering why and how this is actually working. So yeah, one thing, the recovery bootloader is using the lower baud rate, right? So that was using 9600. And the second bootloader is actually also on the different UART. So the second one that I have hooked up. And so it makes sense that we're using different registers. So, but now if we just multiply everything by 4, then we end up somewhere within these registers. Yeah, maybe a closer look at the datasheet will actually reveal something about this. But I find this very interesting right now. It could also be that these are in fact just... okay, so these will be just offsets anyway. So there will be a base address where the UARTs are. And then relative to the base address, we would need to have to add these here. Okay, so let's do this actually. So let's have a look at the datasheet again, which we have open here. And let us see where we find the UART. So we already looked at the memory map here last time. And let's see if we can find the UARTs here. So from a very quick scan, there is this here, HS UART. Do we have anything else? Well, I guess this is it. I'm not sure why it's called HS UART. Unfortunately, we don't have a good table of contents here, so we can't really look this up. But yeah, let's search for UART maybe. Or let's do it another way. Let's look at the table of contents here and hope that we can find it in a very quick second. Interface. Okay. This is usually where I would expect it. But it doesn't seem to be here. Or I'm just overlooking it. Ah, okay, here we go. It's under system peripheral. So here we have UART. Okay, up to 4 sets of UART controller, very nice, blah, blah, blah. It supports the baud rate that we already used on the secondary bootloader 115-200. Okay, but this here is not the... I think it's not the full manual. At least it looks a bit like it's not the full manual. Huh, interesting. Yeah, it's only 137 pages anyway. So usually a manual would be more like, you know, something in the 4 digits realm, like some thousands of pages. So let's see again about the UART. Okay, these here seem to be the GPIOs to use for the UART, which is also handy. Okay, this can take a while to find. What I'm interested in now is the UART's base address. So this here is for GPIO, as it seems. It says GPI. I guess it's just missing the O for GPIO. And because this is getting a bit much, let's search for UART 0 specifically, so we don't run into UART 1. And then let's see what we can find. So, I guess HS UART is for high-speed UART. Okay. Yeah, maybe we would need to find the other UART somewhere else. I don't know. Huh. So this is the GPIO table again. We've already been here, I think. Yeah. Okay. Yeah, then let's look at the the memory map again here. So let's see if we can find these addresses. 1187 quad 0. So do we find these anywhere here? Let's maybe look here. So 1187 quad 0. So the other UART is at 1188 quad 0. So let's put a dot here. And interesting. So this is what we find. UART 0 is 1187 quad 0, and UART 1 is this one here, 1188 quad 0, which are exactly those two here. And here they are given different names. So this here is just UART 0 base address, and this is UART 1 HS base address. So yeah, this is likely, I don't know, it's either an erratum or this is actually fixed, and this here tells us that this here is in fact not a high-speed UART. Anyway, so yeah, now we know this address here. So this is for the recovery bootloader. It's using UART 0. So UART 0 is probably the debug UART, right? So if we look for this again, we will probably find this in use here. Yes, that's in the C file in the driver. And now it actually makes a bit of sense that we have two implementations for the UART, even though they are very, very similar. So I would now assume that if I search for UART 0 base header here, it's not used in the C file, but only in the header. And interestingly, we don't find it at all. Maybe it even has a different name. Let's search for UART 1. And there we go. So we see UART 1 HS base header. Okay. Let's search for any other UART header. Here we go. So there is also UART 321. Yeah. Interesting. Yeah, this is getting even more confusing, especially with the UART 2 and 3. So let's look at these addresses here actually. This is 1243 quad 0. What do we have at 1243 quad? Look at this. Now these are just called UART 2 and UART 3. While these are called HS UART 0 and HS UART 1. Okay. Now it's getting even more puzzling. So do only these here support higher speeds and these here don't, and one of those is used for the on-chip bootloader, like the Mascrom? Or is it like, I guess you never know. So how do we figure out which is actually in use here? So let's search again. And let's see what we have here in the C file. So we wanted to look at that anyway, right? So initially I didn't really want to open the header files. So we're looking for, let's say UART 0 HS base header. Now this is interesting anyway, because here we don't have the HS. And let's search the same way as on the other side. Let's search for UART.star header. Let me clear this again. Okay, so the search result already looks a bit different also. So yeah, we're just missing the HS here. Oh. Interesting. What's also interesting is that these are defined in sys.h. So sys.h apparently has a reflection of the memory map that we also find in the manual here. So yeah, this entire table is probably very much what we have in this file. Let's maybe have a quick look at that. Yeah, so here we have all the different offsets of the different peripherals. like UART 0, UART 1, and so on. This is very interesting. But we wanted to figure out which one is used. So yeah, we have a look at the C file now, and also on the right hand side we're looking at the C file. And what I want to see is, I already have this open. What I want to see is, where is the UART 0 base adder used? Look at this. There is a struct defined here. Well, it's a static const. So UART base is defining those different addresses. So, okay, we'll actually have to search for UART base, and then we find somewhere in our code what we're looking for. And okay, they have the same definition here, except that this here is a U64 and this is a U32, but that's okay. So yeah, UART base is just defined in uart.c. And when we say readle, so readle is for read long. Long is just a size for a value. Then we are reading using whichever UART ID we're passing. So yeah, well, and an offset. So we would have to look at some readl function or some writeL function. And we know that we are printing to the UART, right? So in second boot, at some point we were saying booploader, right? So if we search for boop here now, we see this function being called print k, but print k is actually just an abstraction of the writeL function. So the writeL function sits underneath, it just writes a single character for us. But the print k function can now write multiple characters. So let's see what the definition of print k actually is. Look, we also have that in the uart.c file. So let's see, print k. Print k is doing this here. It's again invoking something else. It's invoking v and printf, and it gets out. That's okay. Then we have s and l. So what is out? Out is a buffer, as it seems. Okay. And v and printf. Is this now using our writeL function? I guess it should. No, it's actually just preparing the buffer. Yeah, and I have to be honest, so this is just preparing the format string, right? So I'm also not too proficient at C. There are nicer languages out there. And now this actually makes sense. So there is another call to something called puts, and puts actually does the output. So what does puts do? Puts, or short for put string, it's writing a string until it's hitting the 0 byte. So the 0 byte is what terminates a string. And it writes every single character using the put character function. And the put character function is defined as, well, this is now using the line status register. It's waiting for the line to be ready, and then it would invoke the serial out function. And the serial out function in turn is defined somewhere else here. Now this here is actually using writeL eventually. So I told you that print k is an abstraction. Now we are already like 5 functions deep in there. So eventually writeL will write a single character to the UART, and it would use the UART ID. So yeah, and now we also see how the UART is being selected by saying UART ID equals 0 up here. So we know now that second boot is using UART 0, and so we should also find something here which gives us the ID of the UART. Let's see if they actually have similar code. I would assume so. Of course not in here. Yeah, it would just have been too easy. Here you can also see the difference. So this is write W for a word instead of a long. And again, it's using ID. But the ID here is being passed as a parameter. It's not a global definition like here on the left-hand side. Okay, so yeah, here we get UART port. Okay, and where do we find UART port? Where do we find UART port? Up here. So yeah, this here is actually using UART 3. So yeah, now in a very nasty way, we figured out that this here, UART 3 is actually our debug UART. So yeah, let's have a quick look again. This here is the recovery bootloader, and the recovery bootloader is using UART 3. Okay, that looks like UART 3 and 2. They are the low-speed UARTs, whereas UART 0 and 1 are the high-speed UARTs. And that explains why we only get to 9600 bauds for the recovery bootloader. Now let's have a quick look if we can find some information on this. UART 3, so these are the GPIO pins used by it. Do we also have some comment of supported speeds? No, it doesn't look like it. Yeah, we're through here. Anyway, yeah, as I was saying, this is not a full manual. It's a bit strange, but I guess it's okay to work with. And we also have a lot of source code for reference. So yeah, this is what we're going to use in the upcoming streams. Anyway, yeah, this was already a very, very deep dive again today. So just for recap, I showed you the following things. I showed you a dump of the mask ROM. I showed you how I could actually obtain that. We had a look at the source code to both the second stage bootloader and the recovery bootloader. And we modified and loaded both of them and ran them. And instead of a bootloader, we had a booploader in the end. All right. So yeah, thank you very much for today. I need to announce now that again, I will have to leave out one of the streams, which is next week, because I will be at Embedded World in Nuremberg. And there will also be quite some vendors there, as I heard, which are talking about RISC-V, and maybe they will release some of their latest chips. At least I heard that the BeagleBoard folks will also be there, and they might have a new board for us. Let's see. So yeah, with that, take care and see you next time in 2 weeks.